Tom Bridgeland from University of Sheffield, giving today a talk. The title is on the blackboard or whatever on first slide, Geometry from Donaldson-Thomas Invariants. Tom, please.
Okay, thanks. Thank you very much, Jan, for inviting me. And thanks everyone for coming. Okay, so what's this about? This is about some ongoing project to somehow use Donaldson-Thomas invariants to define a geometric structure. So maybe it's easier just to sort of carry on a bit and then discuss, you know, why we would want to do that. So right, so I'm going to just scroll down these slides, and it's your job to stop me and ask me questions. Otherwise, I'll be done in 10 minutes. It's too easy when you have it all at your fingers like this. Okay, so this is the general scheme. Let me get rid of this. It's in my way. Right. So we start with some triangulated category D. So the sorts of examples we have in mind are, you know, the bounded derived category of coherent sheaves on some variety, or the Ginsberg algebra of some quiver with potential, for example. And then we can build this thing, the stability space, or the space of stability conditions, stab of D, and this thing is a complex manifold. Okay, and that basically works without any assumptions, but you know, there's nothing tells you that this thing is non-empty. So I guess the main assumption you need here is that the space you're getting is non-empty. When it is, then you get some nice complex manifold. And then in the case that this category is three-dimensional Calabi-Yau, you also, well, you hope that you can run DT theory as developed by Joyce and by Kontsevich and Sogelman, and then get some DT invariants, which depend on your stability condition, which I'm denoting by sigma. So sigma is some point of this space, stab of D, and also on some numerical invariance in Chern character or something like that. And I guess here there are a whole lot of assumptions, but basically you need that moduli spaces of stable objects exist and are well behaved, and that your category is CY3. That's the main assumption. And then really what this talk is about is this next step, which is using these DT invariants to define some geometry on this space of stability conditions. And this again will need some assumptions, and the most important one is that the DT invariants don't grow fast. So let's fix the stability condition, and then we want that the DT invariants don't grow very fast as this point goes to infinity. So gamma lives in some lattice z to the m, and I want it to, these numbers not to grow too fast as gamma gets larger. I'll write a better, a more precise condition in a minute. Okay, and so then we hope, and I should say that this blue arrow, as far as I'm concerned, should really be dashed, because I don't have a construction that, you know, I just have an ad hoc construction which works in some examples. And when it does work, it spits out this geometric structure, which I'm calling a Joyce structure, and which I'm going to explain to you today. Now, I should say that Maxime and Jan, Kontsevich and Sogelman, have a sort of alternative approach, a better approach, which, given a slightly weaker assumption than this, they call it analytic stability structure, but not very different to this exponential growth condition. They can rigorously construct some geometric structure on stab of D, which is quite closely related to what I'm talking about here. It's a weaker structure, I would say. It's more like a germ of this structure. Again, I'll say a little bit more about that soon. So I'm kind of optimistic that one day we will be able to understand this blue arrow that I've got here, but for now I only understand how this works in some examples. Okay, so the plan of the talk is that there's going to be some kind of basics on stability conditions, hopefully go through those quite quickly. Then the main thing I want to do really is explain this notion of a Joyce structure and give an interesting class of examples which are related to basically the Hitchin system. Okay. So yeah, so sort of the main points I want to get across is that these joist structures, they have a perfectly good mathematical definition, and they're rather rich. You should think of them as kind of like non-linear Frobenius structures. And that there is this interesting class of examples of them, which are quite analogous to a sort of complexified Hitchin system. And similarly to the Hitchin system, they're extremely rich with, you know, the tons of questions about these things that you could ask. And in general, in the whole subject, there is so much we don't know yet. There are many unsolved problems, you know, questions to ask about these things. Okay, and then if there's time at the end, I'll try and just talk briefly about the twistor space of one of these joist structures and give a definition of this something called a tau function, which leads to in some further directions. Okay, was there anything else I wanted to say? Oh yeah, I should just say that these three arrows are kind of from different parts of maths almost. I mean, this is all, the first arrow is all about kind of homological algebra. This DT theory is all about moduli spaces. And this bottom arrow, you don't need to know very much about DT theory to start working on this problem. You just need that there are these invariants and that they satisfy the wall crossing formula. And this is really something like complex analysis. It's not, you know, so these three arrows are kind of in different areas. Okay, so if there are no questions at that point, I'll carry on. So, yeah, so the starting point, as I said, is some triangulated category. And I take it to be linear over a field, which I take to be the complex numbers, just because those are the examples I have in mind. And I want this finite type condition, which maybe people would say smooth and proper these days. It means that the Hom spaces between two objects occur only in finitely many degrees, and all these spaces are finite dimensional. So this vector space has finite dimension. And then whenever you have a category like that, the first thing you want to define is this thing, the Euler form, which gives the alternating sum of dimensions of those Hom spaces. And this descends to the Grothendieck group. So it gives you a bilinear form on the Grothendieck group.
Sorry, Tom, it's Maxim.
Yeah. Hi, Maxim.
Yeah, hi. Smooth is not relevant here. It's proper. Smooth and proper. It's like smooth projective variety. You should expect higher than exponential growth. Definitely. You need just proper for this. It's not smooth.
Yeah. Sorry, but here I'm just looking about the X groups, right? I'm not talking about growth of. This is something different.
No. But the smooth is proper. It's correspond to like smooth projective three-dimensional Calabi-Yau.
Yeah. Then you can have quadratic growth like in exponential of quadratic. Yeah.
Sorry, I'm confused now. Are you talking about the growth of these DT invariants, quadratic growth?
Yeah. This sub-exponential growth, it fails probably if you require smooth and proper. Probably you need just proper, like in local Calabi-Yau, you look for coherent shift support.
Sure. Yeah. I should say this. So
the Calabi-Yau itself shouldn't be compact.
Yeah, absolutely. This sub-exponential growth is very important, and it will not hold, or the physicists tell us that it will not hold if this D is the derived category of clearance sheaves on a compact Calabi-Yau threefold. That's right. So actually finding examples where this sub-exponential growth holds is not so easy, but this class of examples I'm talking about here certainly has it. And I think we expect it for like local Calabi-Yaus, but I suppose it's not so easy to prove that. Yeah, thanks. But here I'm talking about something different. I'm just talking about a triangulated category such that the Hom spaces are finite. Nothing to do with DT invariants here. No. Okay, and here's the assumption on CY3. Basically, I just mean that these Hom spaces satisfy this relation, which imitates Serre duality on a Calabi-Yau threefold. And of course, this has the implication that this Euler form is skew symmetric. Okay, so these are the kind of basic invariants you associate to a triangulated category which satisfies this finiteness condition. And then one other piece of data it's convenient to fix is what physicists would call a charge lattice, maybe. So I take some Z to the n, some free abelian group, and I map my Grothendieck group to this group gamma. Okay, and I ask that this Euler form descends to a form down here. The point is that often, well, in many examples, this Grothendieck group is infinite rank, and so it's kind of unpleasant to work with. So, but on the other hand, there is often a natural map like this, for example, the Chern character to cohomology. Okay, so the Grothendieck group of the derived category of coherent sheaves on some varieties, like almost always infinite rank, but it has a natural map, the Chern character, to some cohomology group. Okay, so that it's convenient to just fix that data. And I should remark that I don't necessarily insist that this is surjective. And that can be useful because it means that I can insist that this form is non-degenerate on gamma. You see, it's often the case that this form, I mean, this form could be 0, this Euler form, but I can always make gamma bigger in such a way that this thing is non-degenerate. And sometimes it's useful to assume that. Okay, so once we've got that data, a stability condition consists of, so I denote it by sigma, and it consists of 2 pieces of data: essential charge, which is some group homomorphism from this lattice gamma to the complex numbers, and some full subcategory of semi-stable objects, denoted P, and it's kind of graded by the real numbers. So there's the full subcategory for every real number, but most of them just the 0 category. And these are the we call the objects of these categories semi-stables of phase phi. And these satisfy some simple list of 4 or 5 axioms, which I'm not going to repeat here. But yeah, so that's the definition of a stability condition on a triangulated category. And then the main result about this is that if you consider the space of all stability conditions on a fixed category D, then there's an obvious forgetful map which forgets about this category P and just remembers the central charge, this map Z, which is a map from gamma to C. And the point is that there is a natural topology on this set of stability conditions. It's Hausdorff, and this map is a local homeomorphism. Okay, so of course this space here is just a copy of C to the n. So you have a map from your Hausdorff topological space to C to the n, which is a local homeomorphism. So of course, this space becomes a complex manifold. And I should just say that for later reasons, this is just a little technical remark. This space obviously, or kind of fairly obviously, carries an action of the group of symmetries of your category, group of autoequivalences. And it's convenient to mod out by the action of the second shift. So any triangulated category has a shift functor, and it's good to mod out by that second shift. That actually doesn't affect the central charge. So this map here descends to this quotient. The reason I want to do this is then you have a C star action on M. Otherwise, you only have an action of the universal cover of C star. Okay, so it's kind of convenient to mod out by 2. That's just a tiny thing. Okay, and so the main, the way you say this, to rephrase this theorem, is that if I take a basis of my charge lattice gamma, then I get local coordinates on my stability manifold, stability space, by just taking the central charges of these classes. And so these coordinates will come up a lot in what follows. Okay, so of course this theorem tells you that this complex manifold has a single chart, if you like. And if I choose a basis, these are the functions, the coordinate functions. Okay, so we're going to be looking for geometric structures on this space of stability conditions encoded by DT invariants. But I should, before saying anything about that, I should just say, what are the structures you already have on this space? Well, the first thing is you have an integral affine structure, which is just comes about because you're locally isomorphic to this vector space, which has a lattice inside it. So this is kind of a bundle of Z to the n's inside your tangent bundle, and it's just this thing spanned by these d by dz i's we've got here. Okay, so there's a natural integral affine structure. There's also a C star action, which on the level of the central charges just rescales the central charge. And it doesn't change which objects are semi-stable either. It does have to change the phases. The phases, you know, the labeling P of phi has to rotate, but this subcategory P doesn't change under this action. And finally, in the CY3 case, we have a Poisson structure, which is given by this in coordinates. I mean, it's just because you have a skew symmetric form on gamma. And as I mentioned before, I'm often going to assume that this form is non-degenerate. So in that case, we get a symplectic form, which is just the inverse of this Poisson structure. Okay. So those are the structures we already have on stability space. We have these integral affine structure, C star action, and essentially a symplectic form in the CY3 case. Okay. And then we're going to want to use DT invariants to define further structure, which is going to have to be compatible with this existing structure. Okay, so I'm not going to say anything about how you define these things, of course, but in good cases, for example, if your stability condition boils down to stability for representations of a quiver with potential, then you have well-defined invariants, dt sigma of gamma. So these depend on the class in your charge lattice, that's gamma, and also on a stability condition. And there is this beautiful story that as you vary your stability condition, these invariants kind of remain the same, but then change, you know, undergo jumps as you cross walls, codimension 1 walls in stability space. And that the way they change is controlled by this thing called the wall crossing formula, which means that in principle, if you know all these invariants at one point in stability space, you know them for all other points in that connected component. So the main aim is to, as I said, try and use these DT invariants to define some geometric structure. And this sub-exponential growth condition can be written like this. So if I choose some norm on gamma, or on the real vector space gamma tensor R, then possibly after rescaling this norm, making it bigger, this sum should be finite, where I sum over all points in my lattice. And as far as I understand, I hope I'm correct, I'm sure Maxime and Jan will correct me, that this condition does imply that their condition of analytic stability data, but the reverse implication is not true. So there is some more subtle notion of analytic stability data, so some condition on these DT invariants, which has the brilliant property that if it's kind of constant in connected components, so if you can check it at one stability condition, then it holds automatically for all stability conditions in the same connected component. Okay, it's not at all clear that this relation I've written here is invariant under wall crossing, right? Because these wall crossing relations can be very complicated. You can start with just 2 non-zero DT invariants, and then you can cross a wall and you can have infinitely many non-zero DT invariants. So the idea that this relation, this condition is preserved under wall crossing, there's no reason why it would be. Okay, but Consevich and Soderman have some, you know, have thought about this, and there is some more subtle condition which is preserved under wall crossing. I hope that's correct. So what I've been working with is a kind of ad hoc construction using these things called Riemann-Hilbert problems, which in examples give rise to a geometric structure which I'm about to explain. But unfortunately, there is no guarantee that that these Riemann-Hilbert problems have solutions or unique solutions. It's just in examples you can show that they do. Okay, so but Consevich and Soderman have got some rigorous construction of some slightly weaker structure, which is like a germ of one of these things. Now, I don't want to say too much about this because I don't really understand it. But let me just say one comment for the experts, just for discussion. A lot of this story is sort of driven by an analogy with the theory of Frobenius manifolds. And if we just think in Frobenius manifolds, you often come up with connections like this. So this is supposed to be a connection on P1, on a trivial bundle on P1, with singularities at 0 and infinity. So U and V are just matrices here. So it's some trivial vector bundle over P1. And this has a regular singularity at infinity and irregular singularity at 0. And you can associate to that its Stokes data. And in this story, we're trying to go the other way. We're starting with the Stokes data and we're trying to get to this connection. And I think the first thing that happens is that the irregular Riemann-Hilbert correspondence will tell you that the Stokes data is equivalent to some kind of germ of meromorphic connection. So, which is something like this, which looks like this guy, except that this is just some holomorphic function in epsilon. So there are extra terms in epsilon squared and epsilon cubed and so on. And it's just convergent in some neighborhood of the origin, epsilon equals 0. And then there is this thing, what's it called? Birkhoff extension or algebraization, which tells you that you can sort of go from this to a meromorphic connection on P1. So this is just a germ of a connection at the origin. But then using the Riemann-Hilbert correspondence, you can extend to a meromorphic connection on P1 with a regular singularity at infinity. And then you can try and choose a holomorphic lattice and get to this form. But this will be a kind of, only works generically, you know, so going from here to here is a bit subtle. And as far as I understand, I think, you know, if we change all this to this notion of to the world of DT invariants, where we have to sort of change the group GLN to this group of symplectic automorphisms, then I think what Maxime and Jan are constructing is something which has more like a family of connections of this type, so germs of connections at the origin, whereas what I'm working with is some kind of family of connections like this. And obviously the relationship between these two things is a bit subtle. I mean, there's a restriction map that way, but going the other way is not so clear.
Yeah, actually, since you mentioned it's weaker, we have this kind of axiomatic description of this analytic story. And I remember we had a conjecture that our description is equivalent to considering families of analytic stability data in our sense. So I'm a bit puzzled, because if indeed it's only a corollary of this sub-exponential growth and not equivalent to it, so then it looks like this weaker condition, it covers all known examples, which mean that kind of this global structure may be unnecessary. Of course, yeah. If the conjecture is true, but basically we consider analytic families of analytic stability data, and you will consider something like this. I don't know what the Joyce structure is, but it's some structure on the space of stability data. So you also consider family, your central charge gets changed, and this sub-exponential property holds. I mean, at least you hope that it holds regardless of the wall crossing and other stuff. So it's very closely related, but our example, they cover kind of, at least to me, I don't know, maybe Maxime know more, but they cover all known examples of this, at least in relation to resurgence, cover all known examples, including DT story and other things. So I'm a bit puzzled at this time why you need kind of some global structure. Okay, but anyway, sorry, that's just a comment.
Yeah, no, I mean, I agree. I certainly don't want to say that I've got the right answer and you've got the wrong one. I think you have the right answer. This is like exactly in this context, you would get an equivalence between these two things. So this is the correct data to consider because it's equivalent to the Stokes data. But then in the Frobenius manifold story, you don't end up thinking about these kinds of connections. You do some clever you know, generically, there is some gauge change, a unique gauge change, which will take you into this form. And that's, you know, a Frobenius manifold is really a family of connections of this form, not of this form. And I mean, maybe it's also relevant that when Dubrovin's considering the monodromy data of a Frobenius manifold, he doesn't just consider the Stokes data, he also considers the central connection matrix, which is somehow relating behavior at 0 and infinity. And maybe we need to have some version of that in the DT theory story before we can get to connections like this. But yeah, I mean, for now, all I want to say is that the structure I'm considering is not quite the same as what you have, but it's not very different.
Yeah, actually, Tom, I can comment. We have a paper with Lyudmila Katsarikov and Tony Pantev 10 years ago about this Hodge-Serge aspects of mirror symmetry, and we discussed kind of what I forgot, I think Calabi variations of non-convex structure. It's exactly things with infinite series, and it's Frobenius manifold with nonlinear structure. And if you get some properties called data called framing, which exists in some open domains, then you get exactly the right-hand side with second, first order pole. Yeah, so we discuss this extra difference in theory of Frobenius manifolds between one and another.
Yes, I was just looking at that paper to remind myself about Birkhoff extension, actually. But do you have any idea in the nonlinear case, you know, in this DT theory setting?
Not really. Yeah, no, even in linear case, it's pretty subtle, I have to say.
Yes, yes, I agree.
But I think in this some of the later versions of our paper in the archive, we kind of tried to make analogy with your old story with Lyudmila and Tony, and formulated all these variations of analytic stability in the form which is very much resembled this non-commutative Hodge structure. Yeah, I think.
Okay, shall I continue?
Yeah, sure. Sorry.
No, I'm extremely happy to have these conversations, but I feel sorry for the rest of the audience, maybe. So I should carry on. Okay, so I'm going to say what a Joyce structure is. Okay, so, and this, we don't need to talk about stability conditions yet. So let's just take some complex symplectic manifold. This will end up being stability space. Okay. And so here's the picture. Right, so we just have to contemplate this picture for a minute. So I want to take the total space of the tangent bundle of n and its projection down to n. Okay, so here's the picture. And so then I can think about the tangent space to x. And of course, I can take the derivative of this projection. So that gives me a map down to the tangent space of n, except I should pull back so that everything is on the same space. And then the kernel of this is, of course, just the vertical tangent directions. Okay, so here's the picture. Here's x. It's projecting down to n, and these red arrows are vertical tangent directions. Now, what we want to think about is a nonlinear connection on this tangent bundle. So, so what is that? It's precisely just a splitting of this short exact sequence. Okay, so in other words, it's a way of lifting a tangent vector downstairs on n to a tangent vector upstairs so that it projects back down. Okay, and so the important thing to note is that if I lift this tangent vector at different points in this fiber, there is no relation between these lifts. Okay, if this was a linear connection, you know, there would be some relation here, but there is no relation. Okay, right. But now there's another thing, which is that because this isn't just any old space, it's actually the tangent bundle. There's a vertical lift as well. So if I take a tangent vector downstairs on n, I can think of that as a tangent direction to the fiber, right? Because the fiber is the tangent bundle. The fiber is the tangent space. Okay, so there is a canonical isomorphism here, this red thing. It's just saying a tangent vector to n is a tangent vector to the fiber of this map. Okay, so it's a little bit confusing, but there we go. So it means that if I have one nonlinear connection here, I get a whole pencil of them because I can just add epsilon inverse times this red map. Okay, so I have now a one parameter family of connections, nonlinear connections on this map. And I'm denoting it epsilon inverse just because that's convenient later, but of course, you should think of it as just being t or something. It's just some parameter in the complex numbers. Okay. And then the crucial thing is that I want to assume that all these connections are flat and symplectic. So flat means that locally I can write X as a product of M cross something so that the connection is just the trivial one. Okay, so I mean, if you have a product projecting down to the base, there's an obvious connection, nonlinear connection on it. So this is saying that locally you can turn this connection into that form. That's what flat means, or of course you could say the curvature is zero. And then the other thing is each of the fibers of this map is a symplectic vector space, right? Because we have the symplectic form from M. So I can think about parallel transport of this flat connection, and I ask that those are symplectic maps. Okay, they're not linear maps. They don't preserve. If I do parallel transport, if I take some curve along here and I do parallel transport, I'm not going to get linear maps between the vector spaces, but I will get symplectic maps. Okay. So I'm kind of laboring this because this is the only content, really. This is the structure I'm looking for. A pencil of nonlinear connections of this form on the tangent bundle of M. And you can see already that it's a little bit like a Frobenius manifold, because in a Frobenius manifold, what is a Frobenius manifold? Basically, it's a manifold with a pencil of flat linear torsion-free connections on the tangent bundle. Okay, so we dropped the linear and we've put symplectic instead. So let's try and work this out in coordinates just to see how it looks. So remember we had these, well, let's take some coordinates on M. In the case when M is stability space, we have these natural coordinates, and I assume that they're, oh yeah, so I really am putting myself in that case. Okay, so yeah, what do I mean here? Omega, I want these to be Darboux coordinates, and these are the, yeah, so the symplectic form should be omega ij, dzi, dzj, that's what I mean. Okay, so now X, remember, is the total space of the tangent bundle. I have linear coordinates on the fibers of that by just pairing with dzi. Right? If I have a tangent vector, I can just pair with dzi. So this gives me coordinates on this total space X. And then this vertical lift I was talking about before is just the obvious thing that takes dzi to d theta I. And so what about this horizontal lift? Well, the fact that these things, the horizontal flows preserve the symplectic form tells me that I should be able to write them in the following form. So they have to, the horizontal lift has to project down to d by dzi, and then it has to have some d theta I directions. That's, kind of the vertical stuff. But we can assume that this is a Hamiltonian flow in the fibers. So we can write it in this form, right? This just means it's the Hamiltonian flow for some function wi. Okay. So what I'm trying to do here is lift a vector field on M to a vector field on X, which is the total space of the tangent bundle, so that it projects down to the vector field I started with. So that's what this term is doing. And such that it's kind of, when I integrate the flow of this vector field on X, it should preserve the symplectic form on the fibers, so I can write it in this kind of Hamiltonian way. Okay. So that's for some functions on X. And then the condition that the pencil is flat, it basically means that the bracket, so that remember the pencil is H plus epsilon inverse times V. Okay, so when I sort of do the flatness condition, I will get terms in epsilon minus 2, epsilon minus 1, and constants. And what you find is that first, each of these functions has to just be the derivative of some single function with respect to theta I, and then some system of PDEs for W. So this is just, this is easy. You just look at the flatness condition. Okay, and so these have been well known since the 1970s. These are called Plavansky's heavenly equations, which is a nice name. And I should say that I wrote down these things based on analogies with Frobenius manifolds and so on. And then it was Ian Strawn and Glasgow who pointed out that these equations already existed in the literature, and that was extremely helpful.
So how did they appear in this Plebansky story?
Well, I mean, these people are studying general relativity, right? So they're
Yeah.
studying solutions to Einstein's equations but complex. Yeah, I mean, complex solutions to Einstein's equations. Very much related to kind of work like, well, I guess, yeah, in the UK we would think about people like Penrose School, but yeah, so this comes from work on general relativity. I couldn't say more than that. Okay, and so one of the things you get out of this, which is very easy to see, is you get what I like to call a complex hyperkahler structure. So remember, this is, I should really say, this is on X, the total space of the tangent bundle. So X is a complex manifold, and what I mean is that we have some complex metric endomorphisms ijk of the tangent bundle, and these should all be holomorphic. So everything is in the holomorphic category here. And how do you get these? It's very simple. So the tangent bundle to X is kind of split into the horizontal stuff for this connection H and the vertical stuff. And we've set things up so both of these are isomorphic to the tangent bundle downstairs then, right? Because the vertical stuff was, and yeah. So basically Tx is a sum of Tn plus Tn, or in other words, Tm tensor C2. And now we can just act on C2 with these various matrices, and this gives me the sort of the action of ijk and the metric. So it's a complex metric. And then what you can see is that the condition that this is really hyperkahler. So what you need that ij and k are compatible with the metric and flat for the Levi-Civita connection, so covariantly constant. Those conditions are equivalent to the conditions that these connections are flat and symplectic, that the H epsilon are all flat and symplectic. Okay, so this is an equivalent way of saying the same thing. Okay, so that was just some kind of fairly elementary stuff, right? Which is just some nice way of constructing these complex hyperkahler structures, if you like. But really, it's just a pencil of nonlinear connections, flat and symplectic, on the tangent bundle to a space. And now I just want to say, I mean, this is not so important, but what is a Joyce structure? So just as in the case, it's quite analogous to Frobenius structures. So I mean, a Frobenius structure is basically a pencil of connections on the tangent bundle, but there are some other things there, right? There is some C star action. It's quite a kind of rich definition, and there's some compatibilities between these various things. And the same is true here. So basically there are other, it's nice to put this other structure there and examine the compatibilities. But the other structure is the stuff we already had. So this integral affine structure, or the symplectic form, and the C star action, and then this flat symplectic pencil. That's what a Joyce structure is, all that stuff.
Oh, sorry, Tom, may I ask you before you continue?
Please
This
do.
complex hyperkahler structure can be interpreted as kind of like, again, bundle over CP1 of the symplectic fibers, but without real involution. Is it?
Like twistor space construction.
Twistor space description of usual hyperkahler structure.
Yes, exactly. So I will mention that at the end, hopefully, but that's exactly the case. Yeah. So you can just take X, and what you should do is you should just quotient by the integrable distribution, which is H epsilon, right? So the kind of the image of this connection, H epsilon, where was it? The image of this thing is a half-dimensional subspace of the tangent bundle of X. And the flatness condition tells you that that's an integrable distribution, so you quotient by it. That gives you it gives you a space, Z epsilon, and if you put those together as epsilon varies, that gives you your twistor space. Yeah, so exactly. So it's equivalent data to give yourself some family of complex symplectic manifolds over P1. And it's important to remark that there is no real involution or any of that. So the fibers at zero infinity are not related.
So it's just the same story, but without any real structure. Is it?
Yes, but I mean, just bear in mind that, if you take a real hyperkahler manifold, then the fibers of the twistor space have the same dimension, right? I mean, they really are just that hyperkahler manifold with different complex structures, right? But in this complex setting, the fibers of the twistor space are half the dimension to the complex, to the hyperkahler manifold, the complex hyperkahler manifold. Okay, so, if M had dimension n here, this would have dimension 2n, and then the twistor fibers would have dimension n again, because I would quotient x by this distribution. So the definition of the twistor space is strictly different here.
But also there's some reality condition, yeah. Donaldson-Thomas invariance at the end of the day integer numbers, rational numbers.
Say again, Maxime, I couldn't hear.
But at the end of the day, there is some reality property of Donaldson-Thomas invariance. They're real, yeah. They're real numbers, yeah. Yeah, so there's some evolution around, yeah.
Yes, but I think because I'm working with this kind of conformal limit, I've somehow lost that maybe. Yeah, okay, it's a reasonable point. But you see,
but I think you mentioned kind of, I mean, everybody know that there is the space of stability structures is twice as big as what physicists want. So then, yeah.
Yes. Yes, but yes, that's right. So the twistor fibers I'm getting are probably the same dimension as what the physicists want. Yes. Yeah, that's a good point. Yeah, of course, to answer Maxime's question, there is some reality, but yeah, okay. No, maybe I don't. You understand this better than I. Okay. It's true. So, I mean, at the minute, I'm not seeing any reality structure, but it's true that DT invariants are, of course, real. Okay, right. So I'm nearly there. I was just saying that Joyce structures is this kind of Gothic combination of integral affine structure, symplectic form, C-star action, and this stuff we were considering here. But I mean, just to express this in coordinates, you see, I mean, there should be some compatibilities here, but they're rather concrete things, actually. Remember, there was this Plavansky function which kind of generated the, well, sort of described your complex hyperkahler manifold, if you like. And what these required compatibilities come down to that it should be homogeneous in the first variables, it should be periodic in the theta variables, and it should also have this oddness property. Okay, so I claim these are the right things to consider. This thing essentially comes down to the fact that dt of gamma is dt of minus gamma, existence of the shift function. And this business is saying that really, rather than considering the tangent bundle, well, that's what I say here, rather than considering structures on the tangent bundle of M, you should be considering it on the quotient of the tangent bundle by this integral affine structure. So really, there is this natural C star to the N bundle, and it's really a hyperkahler structure on this that you should be thinking about. So that's the structure I'm looking at. So that's the end of that section. If there's any questions, please ask. And if not, let me talk about some examples. Well, the only real class of examples I know, in fact. The base here consists of, as I'm saying here, the base of these structures is going to be a space of quadratic differentials. So it's going to be a space parameterizing complex curve equipped with a quadratic differential and also with simple zeros. And for now, I'm just talking about the case where the quadratic differential is holomorphic. So Menelaus Zakidis, who's in the audience, is thinking about the meromorphic case. So hopefully we're going to have some theorems about that soon. But for now, I only know how to do this in the holomorphic case, which is, kind of a shame because in many ways, the situation where you allow poles is simpler in many ways. And this space does arise as a space of stability conditions thanks to a theorem of Fabian Heiden, who constructed some CY3 triangulated category such that this space, well, actually, yeah, maybe I was just looking up his results. Actually, it's not exactly this. It's rather that if you take the cover of M where you equip C with a framing, then that really is a connected component of standard D, is the correct statement. So I'm more familiar with this result in the case when there are poles, because then it was a theorem of myself with Ivan Smith. We constructed some CY3 category such that this quotient is the space of curves equipped with quadratic differentials with poles of fixed orders. Anyway, so we're talking about the holomorphic case. So, okay, so whenever you have a quadratic differential, you can consider this spectral curve, which is just given by y squared equals q of x. So here's my beautiful picture of it. So we denote that sigma. It's a branch double cover, branched at the zeros of the quadratic differential, and it has a covering involution sigma. And then you can take a bundle over this space M with fibers given by the anti-invariant cohomology of sigma. Now, there's a natural section of that bundle, because if you have a curve with a quadratic differential, well, I should have put P up a star here. So you can pull back the quadratic differential to sigma, and more or less by definition of sigma, it is then a square, so you can take its square root, and that gives you some one form, an anti-invariant one form on sigma, and you can take it to the Raman cohomology class, and that will give you an element of this. So it's just kind of the period of quadratic differential. And then the theorem, which I think is maybe due to Veach, it's a very classical result, is that kind of obviously this bundle has a Gauss-Menin connection on it, and if you differentiate this section with respect using that Gauss-Menin connection, then you get a map from the tangent bundle, because you have to differentiate in some tangent direction, to the bundle H, and this thing is an isomorphism. Okay. So that's all a very fancy way of saying what people would usually say is that there are local period coordinates on this space M. So remember, M is parameterizing a curve with a quadratic differential, and you get local coordinates on that by choosing a basis for this homology, the kind of the homology group here, and integrating the square root of Q. You see, square root of Q becomes a well-defined one form on the double cover, and you can integrate it around the homology class and get a number. Okay, so that's the existence of period coordinates. Okay. And under sort of Heiden's isomorphism, of course, these period coordinates coincide with the central charge coordinates that you have on stability space. So these are exactly the zi's we had before. And then we have this integral affine structure. Well, it's not very surprising. It's just because you have integral homologies. So you see, now the tangent bundle becomes identified. The tangent bundle the tangent space to M at a point of this moduli space becomes identified with this group H1. And of course, we have integral cohomology sitting inside there, so that gives me some integral affine structure. The C star action is just rescaling the quadratic differential. And since it's really square root of Q that enters here, we should have a lambda squared. And the symplectic form is just, remember, the tangent spaces are just this cohomology, so we can take the intersection form. Okay, so that's all that data, you know, this standard data that always exists on stability spaces. We can see it in this example of this manifold M. So the remaining data of the joist structure is we need some pencil of connections on this. As I said, you should really think of it on this quotient over M. And remember, that extra data is really just a single nonlinear connection. Because once you have one of those connections, you generate the pencil canonically, and then the condition is that they should all be flat and symplectic. So really the extra data is just one further connection. Right, and these are the fibers of this. They're kind of H1 sigma comma C divided by H1 sigma comma Z, and we get this. So the point is that you can represent classes here. So we need to write a connection on this map, and we can represent classes in this cohomology group as via the Riemann-Hilbert correspondence, if you like, as the holonomy of anti-invariant line bundles with connection. Okay, so we think of a line bundle with a holomorphic connection. So the holonomy of that thing will live in here, and that gives you an identification. So to rephrase what we're looking for, I'm going to write it like this. Our moduli space M that we were thinking about was really the moduli space of curves with a quadratic differential. And here what we want to think about is curves with a quadratic differential and a line bundle on the spectral curve with a connection. Okay, there's an obvious projection, and we're wanting to make a connection, a nonlinear connection on this map. So how do we do this? So it's a little bit blimey, I think what's going on right now. It's like right. Okay, so it's slightly subtle how we construct this connection. So the first thing we're going to do is we're going to relate this abelian data to non-abelian data, and then we're going to use the isomonodromy connection, basically. So it's kind of it's well known. What is well known? That yes, a line bundle on the spectral curve gives you a bundle with a Higgs field down on C, right? That's this standard spectral correspondence. And what we need to do is extend it to include connections. Okay, so given this line bundle on the spectral curve, I get a rank 2 bundle on C with a Higgs field, and I've written some appropriate things here. Right, so first you have to twist the line bundle, because line L was of degree 0, so you first have to twist it by some pull back of some spin structure downstairs, and then you push it down and you get some degree 0 rank 2 vector bundle, and it comes equipped with a Higgs field whose determinant is Q, essentially. Characteristic polynomial is Q. Okay, so that's the standard story, but now we want to extend it that if I have a connection on L, I also want to get a connection on this push forward bundle E. And this is a kind of a subtle thing, and I mean, after working out how to do this, I found that it was in a paper of Donaghy and Panter, as you might expect, but it seems to not be particularly well known. How do you do it? You basically, if you pull back this bundle, which after all was pushed down like this, it's almost the same as n plus the covering involution applied to n. So that would be true away from the branch point, and then you have branch points, and then you have this R, where R is the ramification divisor. So in other words, the zeros of the quadratic differential. So you can just extend the connection, you can pull back the connection. So I'm mapping this way. So I have a connection on E, I can pull it back, and then I can just extend it to here, although that might introduce some poles, it will introduce some poles along the branch points. And then I take the component along, just take this first component. Okay, so that gives me a meromorphic connection on this thing, N, and then I can relate that to a holomorphic connection on L by tensoring with, there's a canonical connection on this thing. And the reason is that the pullback of the quadratic differential square root gives me a section here, right? Q is a section of omega c squared. So this is a section of p star of omega c. This gives rise, I can just use this map as a gauge transformation. There's a trivial connection here, so I'll get a connection here. And then I can take its square root, I get some canonical connection on this line bundle, which has poles along the branch locus. And so the upshot of all this is that if you construct the connection on N like this and then do this, you get a nice holomorphic connection on L. Okay, so it's a kind of a complicated story. And what is the thing to say? Oh yeah, so that this map turns out to be birational. So for generic line bundle and connection, there is a unique E in nabla which maps down to this, but it's not an isomorphism everywhere. So there is some subtle stuff going on here. Okay, so, but I mean, obviously that was impossible to follow, but what I'm saying is that the spectral correspondence that you already knew between line bundles on the spectral curve and Higgs bundles downstairs can be extended to include connections, but there are kind of some subtleties involved. Okay, and so this is the final step in the in this proof. There is some big diagram here, which I claim is not so bad as it looks. So each of these is a moduli space, and it parameterizes the things that are kind of in the brackets. So we've just been discussing this map here. Right, so this is parameterizing, we're choosing a curve with a bundle on it, and that bundle should have a connection and a Higgs field. Down here, we're taking a curve with a quadratic differential and a line bundle with connection on the spectral cover, and so on. Okay, so the basic point is that on the right-hand side here, we have a isomonodromy connection. Okay, so this is the kind of important thing, that if you have a bundle with connection on a curve and you start deforming the curve, there's a unique way to deform the bundle with connection so that its monodromy is constant. Okay, that's the isomonodromy connection. It's some nonlinear connection on this map. And it's also symplectic, as it's kind of well known. So we have some nonlinear symplectic connection, nonlinear flat symplectic connection here. This diagram here, this square here is Cartesian, so I can just pull it back to here. And then I push it through these two maps and end up with a connection here. And this map should really have an epsilon labeling it, because it depends on epsilon. And so in this way, we get a family of flat symplectic nonlinear connections on this map, which is exactly what we wanted. If you remember, this map is the same as the tangent bundle divided by the integral lattice. Okay, so this is where we wanted to get a pencil of connections. And so this is how we get it. And so pulling through alpha and beta is definitely non-trivial, but you can generically do it because these maps are generically, well, this is generically a tile and this is generically an isomorphism. It's birational. But of course, you know, bad things will happen where these maps are not isomorphisms. And so the resulting structure you get here is meromorphic. Okay, so I didn't tell you that, but I don't actually get a Joyce structure as I defined it. I get a meromorphic Joyce structure. So it means just the same definition as before, but just the things get poles. So most concretely, that function W, which was supposed to be a function on X, is a meromorphic function. But the kind of understanding the poles and where they lie and so on is sort of one of the interesting and subtle points about these spaces. Right, so so the point to yeah, what do I want to say about this? So I mean, although the definition maybe looks a bit unpleasant, I think of these as kind of a pretty rich geometry. It's quite similar to the Hitchin system. So why would I say that? So somehow it's like a complexified version of the Hitchin system in some ways, in that instead of, so the Hitchin system has a map down to the space of quadratic differentials on a fixed curve, whose fibers are compact tori, right? So here we've got something which maps down to the cotant, maps down to something twice that dimension, right? So not only am I varying the quadratic differential, but I'm also varying the Riemann surface. So this is kind of twice the dimension. And the fibers of this map are not compact tori, they're C star to the n, kind of algebraic tori. So, so everything has been kind of complexified. And similarly, instead of, you know, the other famous thing about Hitchin space is that you get a hyperkahler structure on it. Here we're not getting a real hyperkahler structure, we're getting a complex hyperkahler structure. So in many ways it looks like a complexification. But I should say that it's much simpler than Hitchin space. So, and I think this is what, you know, physicists would say that I've taken the conformal limit somewhere. But really this is a much simpler space. It's because this isomonodromy connection is algebraic, everything here is actually algebraic. And in simple examples, where here I really mean when I'm considering quadratic differentials with poles, there are simple examples where I can just write all this explicitly using polynomial equations. I can write down the metric, I can write down the I, j, and k. You can just write everything algebraically. So, I mean, it's a little bit tricky. You have to write down certain changes of coordinate and so on. But basically, everything can be written down explicitly, which is never the case for Hitchin systems, right? I mean, those are highly transcendental, that hyperkahler structure, and nobody tries to write down explicit formulae or anything like that. Okay, so I would recommend these spaces for further study. I think when you start trying to work out where the poles of the structure is and things like that, you bump into all sorts of the questions that people already have thought about in connection with the Hitchin space, like wobbly loci and things like this. And in particular, one question that I'd really like to know the answer to is this space regular along the zero section? Is the hyperkahler structure regular? It doesn't appear like it would, it should be necessarily. I mean, in that the maps alpha and beta are not well defined there, but nonetheless, in the examples I've computed explicitly, it is. So, and that could have some important consequences. So that's just to say that there are some kind of basic questions about this thing we don't know. Right, how are we doing for time? Kind of time is up.
No, you can continue. There were questions. It's up to you. Go ahead.
Yeah, okay. Thanks. I mean, I've got just a few more slides about this twistor space and the tau function and so on. So maybe I'll just go through those. But I mean, if there's any questions at this point, then please shout out. One thing I should just mention about these is that this is just an SL2 story, right? So a Hitchin space you can construct for any group, and certainly for SLN, right? You can consider higher rank Higgs bundles. Here, you can't really do that because what's important here is the moduli of curves is kind of dual to the moduli of quadratic differentials, right? So, in other words, this space, what a better say to think say is that this space is the cotangent bundle of MG, right? So the space of curves, the cotangent bundle to that is the space of curves with quadratic differential. But if I went to a higher gauge group, like SL3, so here I would not just be considering a quadratic differential, I would also be considering a cubic differential. I would need to sort of generalize the curvy direction so that it was dual to the Q and the cubic differential. And that's kind of a problem I think that's well known in higher Teichmuller theory, but I don't know. I think there are some ideas of Fock and Thomas, but I don't really know the answer. So for now, I've only done this for SL2, and there's a good reason for that. I really don't know how to do this for higher gauge groups. That question also comes up when you want to try and work out what is the right thing, what is the stability, space of stability conditions for those kind of class S theories of higher rank. You need some, we don't even have a guess for the answer. So, for class S theories of rank, for SL2 class S theories, we know that the correct moduli space is curves with a quadratic differential. But for higher rank, we just don't even have a guess for what the space of stability conditions should parameterize, or at least I don't know the answer. Okay, so let me just move on to describing this twistor space. This is a kind of interesting thing you can do with whenever you have a joist structure, and it was what I was explaining earlier. So the first thing to think is I just take X. Remember, this is the tangent bundle to N, the total space of the tangents bundle to N. I have the image of this connection. So this connection, remember, lifts tangent vectors from N to X. So the image has kind of half dimension, right? Because it's got dimension equal to the dimension of N. Okay, so the image of this is some half-dimensional subbundle of the tangent bundle of X. And because this connection is flat, that thing is integrable. So I can take the quotient by this foliation. In other words, I take the leaf space of leaves, and I set that to be Z epsilon. Okay, but now I can do that in a family as epsilon varies, and what I'll get is a bundle over P1 whose fibers are this Z epsilons. Okay, so that's what I've done here. And you know, obviously you can think of that as just the equation of X cross P1 by this foliation. Of course, you know, I'm slightly scared of these things because, you know, I mean, this is not going to be a manifold in general. I guess it's kind of the complex manifold equivalent of a Deligne-Mumford stack or something. But so, you know, I'm a little bit nervous about that. Okay, let's press on. So one of the axioms of this Joy structure business was that there should be some C star action which lifts to X. And the way that works is exactly so that this descends to this twistor space. So this twistor space has a C star action lifting the C star action on P1. So in other words, there are kind of only 3 different fibers of this twistor space. There's fibers over 0, 1, and infinity. And the fiber over 0, so remember this connection was like this, so obviously we have to rescale. And so we're really quotienting by the distribution, the image of V, but V was just this thing which mapped a tangent vector downstairs to the vertical tangent vector to X. So that's really just quotienting X by the vertical direction. So that thing is really well behaved. That just gives me N. Okay, so the fiber Z0 is the manifold I first thought of. So in other words, it's the stability space. But there are 2 other fibers that, you know, we need to think about. And if you think about what happened in the class SA1 case, remember, how did we get these? We got them by, how did we get these distributions? These connections, they were isomonodromic connections, right? So the leaves consist of connections with the same monodromy. So they're kind of parameterized by that monodromy. So it's kind of easy to see that this Z1 should be the character variety. So this is, in other words, maps from the fundamental group of C into PGL2, you know, modulo gauge. So this character stack, I suppose I should call it. Right. And really Z infinity is the same because actually that was also an isomonodromic connection. I'm slightly nervous about Z infinity at the minute, but I think in this case it really is the same as Z1. And so if you think about meromorphic cases, so as I said, I'm sort of, in some ways I'm happier with the cases where I think about quadratic differentials with poles. Then the analog of this is not just a character variety, but it's something like a space of framed local systems, and that thing has a cluster structure. And you know, that comes from the same quiver. So we get this kind of rather remarkable thing in those examples, that the generic fiber of this twistor space is basically the cluster variety, and the central fiber is the stability space. Okay, so I sort of I feel that maybe in the end, at the end of the day, that's really well, it's in a way what we're going to want to do. We're going to want to start with the stability space with the DT invariants and build this degeneration. But yeah, I don't really know how to, well, I don't know how to do that at present. But it's closely related to what Maxim and Yama have been doing. Okay, but for now, I just leave that as a striking observation, and it would be nice if it was true more generally. Okay, and then to finish, let me talk about this thing called the tau function, which I'm writing a paper on just now, so there'll be a preprint appearing soon. It's kind of, again, a piece of slightly experimental mathematics. So the idea is that using one of these Joyce structures, you should define a function, a tau function. So maybe I should say a little bit about the history of this. So somehow, the way I get to these Joyce structures is using some Riemann-Hilbert problems. And I tried to solve the Riemann-Hilbert problems for the derived category of coherent sheaves on the resolved conifold. I was able to solve them. And then I found that the solutions could be encoded in a single function, which had it was an analytic function, and it had the nice property that its asymptotic expansion reproduced the topological string partition function. In other words, the Gromov-Witten generating function. So this was very nice because somehow this kind of analytic, these analytic questions around Joyce structures led to a particular analytic function, which could be viewed as a kind of non-perturbative partition function, because it was an actual analytic function, but its asymptotic expansion was the usual topological string partition function. However, the way I defined that function was kind of a little bit ad hoc, and you couldn't really see how to generalize it to other settings. So I've been trying to think about what is the correct way to define such functions so that they reproduce this nice function in the resolved conifold case, but have a kind of more respectable definition. And this is what I've come up with. So, so first off, I mean, this twistor space has a relatively symplectic form on it. So you can write it down like this, where, so remember we have a hyperkahler structure here, so we have a metric and we have I, J, and K, so we can form these symplectic, well, these closed two forms. They're not symplectic because this guy has a big kernel. But okay, so we have these closed two forms, and we can make this combination. And the point is that this this descends to Z. In other words, you know, we form Z by quotienting by this distribution, and that distribution is in the kernel of this form. So it descends to, this form descends to Z. So, and we get a relative symplectic form on the fibers of Z P1. Okay, and so now the idea is kind of stupid. So what we do is we write down symplectic potentials for each of these things. So by which I just mean one forms whose such a D of them is the corresponding things. Okay, so I just I take thetas whose D is the omegas, right? And then I define the tau function like this. You see, because if I take D of this, then by definition I get 0, because this will just be this equation with x1 equals 1. Okay, so D of the right-hand side is 0, so locally I can write it as D log tau, and that's my definition of the tau function. Now, of course, I haven't defined anything here, because without telling you these thetas, of course, I can change these by D of some function, and that will just change tau by the function, so I haven't told you anything. But the point is that there seem to be natural choices for these potentials, for these symplectic potentials. So we have an Euler vector field which is generating the C star action. So we can contract omega minus with this, and because of you use yeah, I mean, using the Cartan formula, you can see that these are symplectic potentials, just because of some homogeneity conditions on omega minus under the C star action. And then, well, theta 1 is really, you're supposed to be taking a symplectic potential on the twistor fiber Z1. Now, as we just discussed, the twistor fiber Z1 is, in examples, is the cluster variety. So we have kind of canonical coordinates on that cluster variety. Well, we have systems of canonical Darboux coordinates, and every time you have a Darboux coordinate system, you can just write down some symplectic potential just like this. Just the obvious thing. So in the examples of class S, I'm taking the xi's to be Fock-Gonchoff coordinates, and I'm writing down that symplectic potential. And then there's one more, which is the connect. This is the thing, omega plus. Sorry, omega plus lives on the twistor fiber Z infinity, and that's the most mysterious thing for me at the minute. But in examples, what you can do is you can just restrict everything to a Lagrangian. There's somehow a kind of a natural Lagrangian in there, so that term goes away, and then you have your tau function. Okay, so it's kind of some experimental playing around with these things. But in examples, so I basically have some theorems in examples that say that this tau function is a nice function. So as I was discussing before, in this case of the resolved conifold, this reproduces the function that I was thinking about before, which is this non-perturbative partition function. And in the case of the A2 quiver, you can compute everything. So this thing can be thought of as a theory of class S case. It's got poles. But you can compute everything completely explicitly, quite complicated though. And you can prove that this tau here is exactly the Pan-Lavey-1 tau function. I mean, there's a paper by Lissavi and Roussillon where the exact dependence of this on monodrop data is pinned down, and this calculation exactly reproduces their formula, which is nice. So I think this tau function is kind of a potentially interesting thing, but at the minute it's just kind of experimental. Okay, I think I really will stop there. Thank you.
Okay, thank you very much. So are there any questions or comments?
Tom, yeah, actually I have a question. It's about this non-perturbative partition function. If you have non-perturbative, you also get perturbative, you just form power series object, yeah? And
so, say again, Mark.
If you have non-perturbative partition functions, you definitely have perturbative partition function, which is form power series object. Yeah, but this object is already very tricky. We have paper again on airy structures. Yeah, we make some kind of description of this object, but it's really not kind of using this topological recursion roughly, but not direct construction of the object. We don't really have understanding.
Is it because I'm just considering the resolved conifold where there are no compact 4 cycles? That I mean, then maybe that avoids more difficult.
No, I don't think so. No. For compact 4 cycles, it's D4 brains. It makes very complicated story. Even without them, it's still kind of.
Yeah. I mean, the statement here is a rather simple one, which is just that if you follow my definition of tau and you expand, well, so you can make it a function of epsilon as well, just by using the C star action on X. In other words, you have a function on X, you can pull it back to X cross C star by using the action. And then you can expand in epsilon and you will get some asymptotic expansion, because this tau function is some explicit integral, it's some triple sine function, and you can expand it as asymptotic expansion just reproduces the genus expansion for the resolved Gromov-Witten theory on the resolved conifold. But it's really just one example. I mean, I think the same calculation would work as long as there were no compact 4 cycles. I mean, of course, that's a very simple setting. This example is getting closer to work by people like Teschner, who have studied, these Pan-Lavey tau functions and their relationship to non-perturbative partition functions for, again, non-compact Calabi-Yau 3-folds, but ones with compact 4 cycles. But
yeah, I think in topological recursion, like Einar and others, they do not get non-perturbative partition functions at all. I mean,
yeah, but Jan, I think we discussed recently using all this formalism crossing, we get some kind of definition, but it's ugly.
Yeah, but it's different approach. I mean, it's sort of yeah.
I mean, there is one thing here that I find striking, which is somehow the Plebanski function, this W, it's kind of like genus 0 information. I mean, it's just that, and that defines the hyperkahler structure. And once you have that, in theory, you should be able to work out tau, because tau, as I explained here, is just a function of that. So this looks a little bit like some very complicated way of going from genus 0 to higher genus. But yeah, which I also have the feeling with topological recursion that is happening, right? You start with simple data and then you have some machine for producing higher genus stuff.
Yeah, well, maybe some little remark to go from genus 0 to higher genus. It's really some extra data is needed. For example, if you consider genus 0 invariants for Calabi-Yau 3-folds or compact Calabi-Yau 3-folds, it's variation of hot structure, yeah. In Milcom algebra. But if you're interested in F1, genus 1 term, it knows already Euler characteristic, rank of
Mhm.
another cohomology which play no role in this.
No, but for compact you have this attractor points in the moduli space which gives some additional parameters, and for non-compact, do you have it? What's Euler characteristic for toric Calabi-Yau? I think it's a little bit ad hoc, at least if I remember. When you look for the input of D0 branes in for compact, indeed you have something like Euler power of the Euler characteristics of something like Mach-Mayhem. But for non-compact, this power, it's a little bit ambiguous. At least I saw different powers in different papers. So how to define Euler characteristic in non-compact case? From physics perspective, I think it's kind of they little bit confused themselves.
But yeah, maybe just to be more precise about that, I mean, in this resolved conifold case, you can compute this joy structure and this Plabansky potential and so on, and it's very simple. It just basically sees the genus 0 invariance, and it is just this variation of Hodge structure. There's nothing very complicated. The hyperkahler metric is actually flat in those examples, and really the only data is this variation of Hodge structure. But then nonetheless, when you compute tau, you end up with the higher genus stuff. But of course, it's just the same as the kind of Gopa-Kuma-Vafa reconstruction, because here there are no higher genus Gopa-Kuma-Vafa invariants. So you're just saying that you can compute the higher genus Gromov-Witten invariants from the genus 0 Gopa-Kuma-Vafa. That's all that's happening. But still, it's happening in some kind of confusing analytic way. It would be interesting if something similar was happening for more interesting examples. I don't know.
You mean like the Donaldson-Thomas invariants, which are more or less the same as Gopa-Kuma-Vafa? They contain all higher genus Gromov-Witten, and so
in these simple examples.
In this case,
yeah.
Okay. More questions? By the way, in your general formalism, do you allow the space of central charges with non-trivial Donaldson-Thomas invariants to be dense in the plane, or they only can accumulate in some sectors? What we call this? There are gaps.
Yeah, well, of course, I have no real formalism, Jan. I mean, because all I can do is compute some examples, and so I never computed an example like that. So yeah, I mean, that's a problem for you guys, right? Who are trying to prove theorems about. I mean, I would like to start thinking about these problems. You know, so what do you need to know about the DT spectrum to actually construct a joy structure? I would really like to. I mean, I hope I tried to convince you that these joy structures are, natural and have nice properties, particularly this kind of twistor space and so on. So now I would really like some rigorous construction of them. But yeah, I haven't thought about these issues about dense active classes and things like that. I've just been computing some examples. So.
Okay, so more questions or remarks or comments, whatever. Last chance. Okay, if not, Tom, thank you very much for very interesting talk. And yeah, so if there are no more questions, so this is it for today.
Yeah, okay, well, thank you all. Thanks for listening, and it was very nice to see you. And